So this is part 2 of a 3-part video, and in this part 2 we're going to be finding the potential function f of xyz of a three-dimensional conservative vector field f of xyz. Okay, now just to recap what we did in the first video, and the link to that video is in the description to this. So we got a vector field f of xyz, which is f1i add f2j add f3k. It's conservative if and only if the vector is the gradient of some scalar function, which is our potential function, i.e. what that means is the partial derivative with respect to x of our function f is equal to f1 here, and our partial derivative of the function with respect to y is f2 here, and our partial derivative with respect to z is f3 here. Okay, now what we have to do, and what we did in the previous video, was first of all test that it is a conservative vector field, and the test for that is if the curl of f is 0, then f is conservative. Okay, so that's a recap of what we did yesterday. So what we're going to do today, we're going to go straight on to a question. Okay, so the question is, confirm that this vector field here, which is described by this vector here, is conservative, and thus find its scalar potential function. And in the third video we're going to do something very clever once we've done all of this, but in this particular video, first of all, what we've got to do is find the potential function given the vector field and given that it's conservative. Okay, so the first thing we've got to do is confirm that it is indeed conservative. So from the previous video we know that that is means that the curl of f has got to be equal 0, which is the determinant I, j, k, partial derivative with respect to x, partial derivative with respect to y, and partial derivative with respect to z, f1, f2, f3, where this here is f1, this here is f2, and this here is f3. And basically that boils down to, once we've expanded it all, that we have to show that df3 dy is equal to df2 dz, which is this mini little part of the determinant, and we have to prove that, or show that d f3 dx is equal to df1 dz, which is this mini part of the determinant here, and we have to show that df2 dx is equal to df1 dy, which is this final one here. Okay, so all we need to do is actually just work them out. So let's go. Right, so df3 dy, sorry that the functions are actually off the screen, but df3 dy is equal to 3x squared. So what all I'm doing is I'm just taking the derivative, partial derivative of that one with respect to y in this case, and then this one with respect to z, sorry, not that one, this one with respect to y, and this one with respect to z. Okay, so df3 dy is 3x squared plus y, and what we got to do here is we've got to do it with, in fact I can keep it on the screen, can't I? There, I'll do it like that, yeah. So this one we'll do by the product rule, so that will be y x squared z e to the xyz add x e to the xyz. That's just differentiating that partially with respect to y using the product rule, add cos z. So that is the derivative of that one there with respect to y, and then unfortunately, sorry, it's going to have to go off the screen, so df2 dz, you're just going to have to scroll up, is 3xz squared add x e to the xyz add zx squared y e to the xyz add cos z. That's just differentiating that one partially with respect to z, and we can see that those two are indeed the same. Good, so that's that one solved. Now we have to do df3 dx. It's just a bit time consuming, this confirming that it's conservative, but it has to be done. So now we are differentiating partially this one with respect to x, so df3 dx is 3yz squared add xy squared z e to the xyz add y e to the xyz, and then we have to differentiate partially f1 with respect to z, and that equals 3yz squared add y e to the xyz add zx y squared e to the xyz, and we can see again that these are identical, so they're the same and they are the same. And then finally what we got to do is we got to do df2 dx, and that is partially differentiate f2 with respect to x. That gives us z cubed add ze to the xyz add xy z squared e to the xyz, and the partial derivative of f1 with respect to y is z cubed add ze to the xyz add yx z squared e to the xyz, and again that's the same, so we have proved that is the same, that is the same, and that is the same, so we at least know that this is conservative. So then what we've got to do is find the scalar potential function, which is actually what the main purpose of this video is about. So I'll tell you what, let's go on to a new page here. Okay, so we know that we have our function f, and we have our function here f of x, y, and z, and that's our scalar potential function. Okay, so we know that df dx, we've already said this at the top, is equal to f1, and df f dy is equal to f2, and df dz is equal to f3, i.e., so let's just write them out. So that's df dx equals, all I'm doing is I'm just copying from the thing, so we've got it. So that's yz cubed add yz e to the xyz minus sine x. That's basically this one here, and I'm just going to copy the other two as well. So therefore we have also df dy, partial derivative with respect to y, is xz cubed add xz e to the xyz add sine z, and then we have df dz is equal to 3xyz squared add xy e to the xyz add y cos z add 2z, and let's call that equation here 1, and let's call that equation here 2, and let's call that equation here 3. So this is what we're going to do to find the potential function f of xyz, subject to these three criteria here, which we are given, and we know because f, the capital F, is a conservative vector function. So step one, what we have to do is, so step one is we integrate df dx with respect to x, okay? And then what we're going to do is we compare it to, right, so we integrate, step one, we integrate df dx with respect to x, so that gives us, all I'm doing is I'm integrating this, so that gives us that f equals x, y, z cubed, add, I'm just integrating this here with respect to x, e to the xyz, add cos x, add, and this is the interesting bit, g of y and z, because this is the partial derivative with respect to x. So any functions or subfunctions of f which were just a function of y and z would have been eliminated when we took the partial derivative with respect to x. So when we integrate, we know that the, if you like, constant of integration is going to be some function of y and z. Okay, so now what we're going to do is we are going, so step two, is we are going to differentiate that with respect to y, and then we are going to compare it to equation 2 up here. So basically, let's have a look. So we got f here. So now we're going to differentiate what we found there. We know that that is basically what f is. We're going to differentiate it partially with respect to y. Okay, and that gives us xz cubed add xz e to the xyz add, well, that's only a function of x, that disappears. Now this one here, partial derivative of g of y of z, g of y and z with respect, whoops, sorry, my apologies. Let's just rub that out because that is a bit of a mess. There we go. With respect to y. Okay, now what we're going to do is we're now going to compare this to equation 2 here, and basically we'll see that we got the xz cubed, we got the xz e to the xyz, and we got a sine z. So clearly d g y and z dy is equal to sine z. So dg of y and z dy equals sine z. And again, I better just make sure that I've got that right. That is a y there, because it is important, this, so that's a y. So dg of y and z dy is equal to sine z. And so therefore, when we integrate this, we get that g of y and z equals, when integrating it now with respect to y, integrating it gives us y sine z add what we'd call a constant, which is going to be a function of z alone. Because when we differentiate this partially with respect to y, any function of z alone will disappear. So now we know that our function, moving this function here down here, we know that f equals xyz cubed add e to the xyz add cos x add, well, we know now that g of y and z is equal to y sine z add sum h of z. So we're almost there now. So now we're on step 3, and I think you know where we're going on this. So step 3, what we're going to do is we are going to differentiate that f with respect to z, and then we are going to compare it to our third equation here. So let's differentiate it with respect to z. That gives us partial differential of f with respect to z. This one here, we're moving that down here, is equal to 3xyz squared add xy e to the xyz add y cos z, which is that one. This one here just goes to nothing because that's only a function of x. Add, well, the partial derivative with respect to z of h of z, but we can actually write that as just the normal derivative because there's only one variable there, so we can just write that as dh dz of the function h of z. Okay, and now what we're going to do is we're going to compare that to equation 3 here. And unfortunately, we're going off the screen, but basically that shows us that dh dz, so dh of z dz is equal to this thing here, which is 2z, and therefore, so h of z is equal to z squared plus a real constant of integration. That is actually a constant of integration, which we add in right at the end. So basically now we have our potential function. So therefore our potential function f of x, y and z, we can bring it down from here, is equal to x, y, z cubed plus e to the x, y, z plus cos x plus y sine z plus, we now know what h of z is, z squared plus c. And that is our scalar potential function. And we have our answer. Okay, phew. It is a little bit long-winded, but as long as you follow these 3 steps, you get your answer. Now, just as a check, what we can do is we can differentiate f with respect to x, we can differentiate it with respect to y, and we can differentiate it with respect to z, and we had better find that the 3 differentials are this vector, otherwise we are in deep trouble. So let's just differentiate those. So df dx equals yz cubed. What I'm doing is just differentiating the solution now with respect to x. Add yz e to the xyz minus sine x. That's the differential of our function that we found with respect to x, and that agrees with our vector. And then df dy is xz cubed add xz e to the xyz add sine z, and that agrees with our vector f as well. So that's f1 and that's f2, and this had better be equal to f3, and that is, let's just differentiate it there, that'll be 3xyz squared, add xy e to the xyz, add y cos z, add 2z, and that agrees with f3. So we've got to check that we do now have our scalar potential function. Okay, well, I hope you found this useful. So this is part 2, and just going right back to the beginning now. Now that we know how to test for a conservative field, and now that we know how to find our potential function, we can do something very clever involving vector line integrals in the next video. So look out for that. Okay, well, if you enjoyed this, please press the little thumbs up button and subscribe to the Gracie Academy YouTube channel. Thank you.